So you may have heard this MPI plus thread performance. Thread multiple performance is horrible comparing to process only MPI. This was true and still true for some older versions of MPI library, because optimizing MPI plus thread is pretty challenging. So here's some suggestion that I have for everyone if you want to do thread multiple communication. Because by doing this, you may be able to get a huge performance boost on MPI library that actually well optimized for MPI thread communication. So as recall, the core problem with MPI plus thread is that the MPI has no concept of the thread itself. It doesn't know if two MPI operation happens is from the process and it happens in this order as intended, or is it because these two MPI operations are issued by different threads and the order is just a coincidence of the scheduling. So MPI would always have to take the conservative approach and assume that these order is intended. So in order to preserve that ordering, it has to do a lot of extra work to make sure the thread safety and these orders maintained, and especially on the receiver side, when the message is coming in, there's no way to know that if they are the ordering is important to the application. So MPI has to do a lot of things to serialize the operation. So so the core guideline is we want to expose the thread level parallelism to MPI. So we kind of letting MPI know that there is some level of separation between these communication from different threads. One technique is using different communicator for different threads. So a quick example here is basically now I have a 4th thread, and suppose they all want to communicate using MPI COM word, but instead of letting all of them using MPI COM word, I'm going to create duplications of MPI COM word for each of the threads. So for these threads, although they're talking to the same group of process, but the communication happens on different communicators. And inside the MPI library, then we know, oh, these traffic and that traffic are on different communicators. So they're isolated. The ordering between them are not important. And for advanced MPI libraries, it's even possible to map these communicators to different network resource, hardware resources for network. So we can further eliminate any serialization and the locking needed when two communication when two threads accessing the same hardware resources. So that's one way. And sometimes another way to expose this kind of threading parallelism is using instead of using different communication, you can also using different peer ranks and tags. So this is basically play with the message matching part for the point-to-point communication, where like I mentioned, you can use the tag as a thread ID, so you can make it clear that this is thread 1 to the thread 1 on the other side, so it doesn't get intercepted by a different thread. And same thing inside MPI, we can also use this information to isolate traffic. Yeah, and another thing is related to the wildcard receive. So when you do MPI receive, you can use any source and any tag as the source of a tag. So basically, this the wildcard receive basically allowing this receive operation to match with any with with the send operation coming from any rank or with any tag, it's really convenient to use them. But on the library perspective, it's really hard to optimize them for multiple threading. The problem is that when you do from the receive perspective, when the message arrives, there's no way that to know whether this is order intended by the application or is just coincidence of the thread scheduling. So like I said, MPI has always took the conservative way to assume that this is what the application wants, and to preserve that ordering, which means all these operations from different thread maybe, but has to be serialized on the receiver side, which slows the whole thing down. So, but the good thing is we have these info hints that you can use when you create a communicator or set into the communicator that's saying, I'm not going to use these wildcard receives on this communicator. And in that way, the MPI library will know, oh, for this communicator, the ordering doesn't matter. I can do as much optimization as possible to optimize this for thread multiple communications. So there's that. So like I mentioned, once the user use these technique to expose the threading threading parallelism, the MPI library will be able to optimize. One way we do in MPICH library and all other MPI implementation that build on top of MPICH is what we call a virtual communication interface, a VCI. So this is basically an abstraction of the hardware network resource internally. And what we do is for these isolated traffic streams, we can basically map them to different VCIs. So so there will be no contention between these streams, and there's less locking, unlocking, thread safety overhead associated with this. And yes, with these recommendations, we even have an exercise to apply this. Basically, is if you finish if you're very fast with the code and finish the thread multiple version of the stencil code, you can further optimize it into a thread multiple, but with multiple communicators. Basically have each communicator, each thread using their dedicated communicators for data exchange. So again, solution is over here. So here's just some performance numbers that we can show how this exposing parallelism can help improve the performance and benefit from optimized library. So when I say the MPI plus thread performance used to be really bad, it's all comparing to the non-threaded MPI communication. Means if you have 16 core instead of having one process and 16 threads, we're comparing it to 16 processes, and each process is single threaded. As you can see, basically with this multiple communicator optimizations, with an optimized MPI library, we'll be able to achieve the bandwidth and message rate that is close to a thread single, which is basically is the process only MPI communication. So that's essentially that's the ultimate goal. While your current MPI implementation may not have these optimizations, but the bottom line is always use this practice, because when the same code, if you use this practice, it does not, if the library is not optimized, you're not losing any performance. It's just but if the code is run with optimized MPI implementation, you'll automatically benefit from it. So that's why I would recommend always have this practice in mind when you design your thread multiple MPI applications. And there's just more performance numbers. Gonna skip that. So that wraps up the section on MPI plus thread. So just to summarize, there's the main goal of having MPI plus thread is to either reduce the complexity of communication or having more efficient memory usage. But your application might have other needs that dictates the use of threads depending on the problem. And from MPI perspective, all you need to do is initialize your application with MPI init thread and select one of these 4 thread model. Actually one of 3 because single is no threading. But do remember if you want to use MPI thread multiple communication, there's ordering and other correctness considerations that you need to be careful of, and try to apply these practice that use independent communicators and independent resources between threads, so it can benefit from an optimized MPI library. So okay, so I see there's a question says, what is the scope of MPI info set? So MPI info set is so the MPI assert no any source is set per communicator based. So the info set is taking a hint and the handle. So we can set handle to window, but in this case we're set handle to set info hint to communicators. So yes, that hint is per communicator based. Okay, so there's other questions. Should the MPI thread function, MPI init thread or thread be used in MPI plus CUDA program? No, it's only for thread safety. If you use CUDA, we'll see in the next part of the slides. CUDA has you don't need special MPI init for CUDA. Okay, conclusion is it highly encouraged?
And Yanfei, can you say why there MPI plus CUDA?
No, I'm just saying the init thread is for MPI plus thread. So if you just use MPI plus CUDA without any thread, you don't need to use MPI.
Yeah, so I think people are thinking that GPUs have so many threads, and so those threads are different. Those are different.
Yeah, those are different threads. These threads are CPU threads. MPI plus thread in this context. So the conclusion is a highly encouraged to carry out communication with threads instead of doing communication with MPI process. Actually, no, there's no one rule that fits all, right? So the rule of thumbs is think about your application. Does it need thread or using thread is beneficial to it? Because I mean, if you only think about using thread, because you also have to deal with the synchronization issue that with thread itself, regardless whether you use MPI or not, right? If you're trying to use multi-threaded model for your application. So the first question would be why would you want to use thread? What are you trying to gain, right? So for some of the application, it has a huge data that need to be shared among different processes. In that case, you can also use shared memory, right? If you just need to share data, in that case, you basically controls what data is being shared, which makes the part that you don't want to share much easier to program. So just using thread has other consideration that you need to think of. And also, because we have these different threat safety levels, you can always start with a simple, MPI threat funnel mode, where it's not too complicated in terms of communication, but you can try out the threads on your application and see if it actually benefits from it, and then decide whether you want to move further to a more complex threaded multiple model. Yeah, I think that's my recommendations. Okay, so if there's no other questions, I'm going to move on to MPI plus accelerators or to a specific MPI plus GPU. The plot shows MPI thread perform better. Okay, which are you referring to this one? Yeah. So this figure is actually, if you look at the number here, this light blue line is thread single, means no thread. This is actually the best performance if you look at the message rate and also the bandwidth. It's covered there, but it's there. It's almost the best performance. So and if you compare to the MPI plus thread multiple with no isolation practice, performance is not that great. But the takeaway of this figure is, if you use multiple communicators to isolate the traffic between threads, and on an optimized MPI implementation, you get close to MPI thread single performance. So you benefit from you have all the goods from the thread, but not paying the high costs that you used to associate with MPI thread multiple communication. Okay. Well, what reason for thread funnel to performing so badly? Well, I think this is mainly related to the locking internally that was used in MPH implementation. Okay, so the next part of our tutorial, I'm going to talk about MPI plus GPUs. And in this case, I'm using NVIDIA GPU / CUDA as example. So as you probably already know, that GPU has CPU are kind of designed for different kind of workload, and GPU has a lot of benefit that we care about in high performance computing, where we mostly because it's high performance and power efficiency nature. It has been widely adopted, as in fact 6 out of 10 of top supercomputing system today is using GPU as their main processing unit. So and all the upcoming US based exascale system is going to be GPU based. So GPU for program model for GPU, essentially depending on the vendor of the GPU, you'll be using either CUDA or if you have an NVIDIA AMD GPU, you're using ROCm and HIP, and there's also, you can also use OpenACC or OpenMP offloading to programming with GPU. So these are all the options that are available today. But so far in this tutorial, we're going to just focus on the NVIDIA CUDA as our example. But note that these example can be ported to different GPU program models in a similar fashion. So the core problem in programming GPU is that GPU has separate memory, and how the data, and the MPI is dealing with communication, moving data around, and how do we access the data of a GPU memory, move it in between the CPU and GPU and across the network, right? So so the simple answer is, yeah, it's for most of the modern GPUs, it's you can do that. You can do the communication with as if it's a non-GPU machine. But in reality, if you go into the detail, it actually depends on the version of the generation of your GPU hardware, the version of the driver, and CUDA library and low-level library, and what the MPI implementation is capable of doing. So it's fairly complex, but because it has been MPI plus GPU has been around sometime, so it's for most of the cases this is it's already supported. So the core idea is this unified virtual addressing basically is it's basically is mapping the memory of the CPU and GPU into the same virtual addressing space. So you can so the application can access these different memories in the same fashion. So, and this is also what a GPU-aware MPI library is built on top of. So, so there's different ways to support data movement. So the simplest case is that we can, in order to send the data from a GPU memory over network, one simplest way is that we create a temporary buffer or internally inside MPI library on the CPU memory, and we can copy the data out to this temporary buffer and send that temporary buffer over network. This implementation wise, this does not require any special feature because these are just CPU CUDA mem copy between the host and GPU memory, and then after that is just a regular MPI operation that moves the data from main memory. Okay, but apparently there's overhead associated with this because depending on the buffer location and the feature that it and what kind of memory region that the GPU can directly DMA into, there's maybe double one or more temporary buffer needed. But if you do have a latest GPU that has the GPU direct RDMA, then the communication can happen in a zero copy fashion, where the GPU memory would directly, where the network card can access the data on the GPU memory directly. Okay. And also that is for internal communication. Another aspect of this MPI involving GPU communication is the intranode one. So so most of the MPI implementation, when you do communication and the two process happens to be on the same node, the MPI library will be able to use the shared memory to move the data instead of go through the network card. So that would be a lot faster. So with GPU, one of the from MPI library, what the MPI library can do is try to one is to move the data from the GPU memory into this shared memory, and then go to then on the other processor just read from the shared memory. Although this involves extra copy, and an alternative solution is I don't have it here. Alternative solution will be like using the GPU IPC functionality, where the GPU that belongs to another process can directly read the memory of another GPU. So the GPU on the process 2 can read read from the memory of the in the GPU of the process one. Okay, so and also there's other ways to provide a simply used abstraction for supporting data movement between the CPU and GPU. One of the examples is this heterogeneous memory management, and proposed and available in Linux kernel. Basically is instead of having this explicit memory copy, it lets the operating system to handle the data movement by creating page fault. Now, for example, if the data is on the GPU memory and CPU wants to access that data, it will trigger page fault, and the operating system is going to move the data move the page from the GPU memory into the CPU in order for CPU to consume the data. So this is actually it's simple to program, but unfortunately with this in MPI plus heterogeneous memory management is not a very good idea because one is having this automated page migration is really hard for communication to work on, because the network card need the memory page that contains the data to be pinned down in the physical memory in order to for the network card to send it. But at the same time, this is actually conflicting with this operating system guided page migration, and it's also basically potentially add the overhead of page migration when you do communication if the data is not on the desired location. For example, if the page is on GPU, and when it's doing communication, it will first pay the page migration costs from the GPU to the CPU before it can be sent over the network. Right. So that's not recommended, and I don't think our MPI is well, MPI can practically use this, but it's not recommended. Okay. So like I said, depending on where how MPI assumes the location of the data, there's overhead of page fault and page migration associated with that. So here's how you do it with CUDA, MPI plus CUDA. So just a quick overview of what programming with CUDA is like. So basic CUDA is the NVIDIA's library and runtime now evolves into a complete programming environments provided by NVIDIA that allows you to write programs for GPU kernel to run. So essentially, for your computation, in this case, in this example here, we just have a simple function that needs to be called, performed by GPU. So we write it as a GPU kernel and launch it on the GPU. And before the launching, we need to initialize, create a buffer that is for the computation, and also initialize with the data that is on the host. And then we, after the kernel is finished, we just do a memory copy, and to read the results. Okay, so that's just a quick overview of how CUDA programming is working. So the MPI plus CUDA is this is where things get a little bit complicated. Okay, so depending on the version of CUDA and the GPU direct supporting on a GPU, you may or may not have some performance implications here. So with MPI plus GPU direct, what you can do is you can use the device buffer in MPI communication. So as the example shows here, we just took the device buffer that the kernel is working on and use it in MPI send. But depending on the CUDA library version and the GPU direct support, internally MPI may have to create a temporary buffer for the data as a in the host memory in order to move the data around. But if you have a CUDA that is a CUDA version that is new enough, basically this is supported since Kepler and the CUDA 5. The GPU memory can is directly accessible to the network card. So in that case, if you have a compatible GPU and compatible network card, then the code is the same, but internally it can skip the copying between CPU and GPU memory and CPU memory, and just go directly to the network. And also with the even newer CUDA, there's introduced this unified memory model where the page is being migrated between the CPU and GPU. I mean, from the MPI programming perspective, it's the same. You don't have to worry about where exactly this buffer is. You just use this buffer in communication, and then the GPU-aware MPI would handle it. Just one thing to notice here is that you need to, between the GPU kernel launch in this line and the MPI ISEN operation, you need to do a CUDA stream synchronize on the stream that the kernel is launched. The reason is that the GPU kernel launch step here, this operation is asynchronous to the CPU. So if without this stream synchronize call here, the MPI ISEN will start the GPU kernel launch will start and then returns when the kernel is launched. But at that time, the kernel might still is most likely still running. But the GPU MPI ISEN is not aware of that. It will try to send the data immediately while the GPU might still writing data into that buffer. So that's why you need a explicit CUDA stream synchronize here. There's ongoing work in MPICH library and also in other MPI implementations that trying to make the MPI not only GPU aware, but also stream aware, which can sort of avoid this explicit synchronization between the CPU and GPU. So just to summarize, these are the states, just a reference table for you to look at if you want to know what exactly is supported and how it's been performed in potentially inside of MPI. So most of the machine today will have connect X5 network and a new enough GPU. So it's most likely you can use GPU communication and take the zero copy route where the GPU network card is accessing GPU memory directly. Okay, I see there's some question. So so can you give any more information about investigation into stream aware MPI? Yes. So GPU aware MPI is mainly about MPI being able to use GPU buffer. So the stream aware MPI is allowing MPI operation to be killed on the GPU stream. So it's getting ordered correctly with GPU operation. So this improvement in MPI is to address the synchronization, essentially the synchronization issue between the MPI operation and the GPU. There's also efforts going on to make the MPI library being able to invoke inside of a GPU kernel. So instead of launch kernel and wait the kernel to finish and do some communication, you can even have fine-grained communication that happens inside a long-running GPU kernel. That's also ongoing. And in fact, if you look at the what NVIDIA is offering for the OpenSHMEM library, there's NVSHMEM that does exactly that. Although it's for the OpenSHMEM program model, not for MPI, but as you can imagine, in the MPI world, we're also trying to do that. So are these all supported for OpenACC as well? Yes. So what I talked about here is also applied to OpenACC in terms of accessing the GPU buffer. Okay, let me see if there's another question. Okay, is there any way to query the MPI library regarding which mechanism being used for inter-GPU communication? Whether it's through RDMA or via copy on GPU. So for MPI library, there's no standard way to query that, I would say. In fact, I don't think we have something to query for the specific support of the GPU. But if you would look at the slides here on slide 197, basically this is just a guideline of what is available depending on the CUDA version and your and like I said, today the latest CUDA is CUDA 10 or 11. I don't remember the exact version number, but like this table is showing that after 2014, it's already have after 2012, it's already have the GPU direct RDMA support, which does a zero copy. So if you're using a latest a new GPU with latest CUDA, and you should get this. And well, although in some extreme cases where the correct kernel module is not being installed or being loaded into the kernel, you may or may not be able to use this. But I think that's beyond the scope of this tutorial. Okay, so I see that's all the questions. And what's the okay, so I think we're right on time here. So yeah, so just to summarize, basically in today's HPC system that with GPU, you can pretty much just use a GPU buffer in communication the same way as you use a CPU buffer, as long as it's MPI, a GPU-aware MPI implementation. Yeah. So so we have examples for the central code using GPU on Cooley. Okay. But in order to use that, you need to use the NVPeach and the CUDA-aware NVPeach in on Cooley. So you need to load this module